What if a deliberately engineered protective layer on the surface of a battery cathode material could extend its life? That's exactly what the artificial cathode-electrolyte interface does. Hello, and welcome to the Rigaku vlog on industrial battery advancements. I am Zijun Wang, a materials scientist and R&D consultant with years of experience helping battery companies solve material and quality challenges. I cut through research, industry news, and policy updates to bring you the latest battery updates in under 10 minutes. In this episode, let's take an overview of the artificial cathode-electrolyte interface, or CEI. The natural CEI forms spontaneously on the cathode surface when the battery undergoes repeated charging and discharging cycles. The electrolyte breaks down at high voltages, releasing byproducts that accumulate and eventually form a passivating layer on the cathode. The uncontrolled formation of the natural CEI often leads to non-uniform and unstable layers that may not effectively protect the cathode from further reactions. This contributes to performance degradation, increased impedance, and capacity fade over time. To solve these issues, the artificial CEI is deliberately engineered, typically applied to the cathode surface prior to the battery assembly. Various methods is used, including chemical vapor deposition, atomic layer deposition, solution-based coatings, or dip coating methods. The coating is to ensure uniform and controlled coverage on the cathode surface. It helps minimize side reactions between the cathode and the electrolyte, maintain battery capacity, and improves the overall safety of the battery. Samsung SDI published a patent in summer 2024 describing an approach to make coated cathode material to meet above-mentioned criteria. Let's dive into it. Here's a synthetic example of a cathode material with coating. Nickel-cobalt aluminum hydroxide particles with selected diameter are used as the precursor. It's heated to 500 degrees Celsius for half an hour in oxidative condition. During this step, thermal decomposition occurs. The weight loss is understood to be a stepwise loss of loosely bound water and dehydroxylation. In the second step, a mixture of chemicals is added into the intermediate oxides, including 1.1 equivalent of lithium hydroxide, 1 molar % of lithium sulfate as a flux agent, half molar % of hydrophobic silica, and half molar % of lithium phosphate. The mixed material is heated at 800 degrees Celsius under 2 atmospheres for 15 hours. Single particles of NCA cathode with silicon, sulfur, phosphorus coating are obtained. It's mentioned that there is a synergetic relation between the flux agent and silica. If only sulfate-based flux agent is used, sulfur do not remain on the surface, and there is no protective layer on the particle. Another note is that the product made from hydrophobic silica performs better than that from hydrophilic silica. The hypothesis is that, first, hydrophobic silica has better dispersion during application. It reduces unwanted agglomeration. Second, the alkyl chain decomposes during heating, leaving behind pores or channels to accommodate other species. It could maintain good electrolyte permeability and allow for lithium-ion transport while protecting the NCA surface. In an example, one more step is taken to coat cobalt on the outmost layer. Cobalt hydroxide is converted into cobalt oxides on the particle surface and provides additional stability. Besides cobalt, zirconium or a combined coating is also explored. There are several ways to obtain structural information about an artificial CEI. Hadaf stem imaging combined with an FFT pattern can quickly provide qualitative or semi-quantitative crystallographic insights. This high-angle annular dark field mode gives real space images with Z contrast, which is useful for detecting compositional variations. Applying a fast Fourier transform converts this image into reciprocal space, revealing periodicities that correspond to the projected lattice spacings of the crystal. Bright spots in the FFT represent reciprocal lattice vectors, whose positions yield d-spacings and zone axes. In this example, the PNMA space group indicates that the LCPO adopts an orthorhombic structure. To obtain more precise crystallographic information, selected area electron diffraction can be performed on the particle surface if the feature size permits. This technique provides a direct experimental measurement of electron scattering in reciprocal space. When carried out using micro-ED with a sample tilt holder, the reflections can be indexed for full space group determination, orientation, and symmetry. Intuitively, this illustrates how these layers contribute to mitigating nickel dissolution. At high charge, surface nickel exists mainly as unstable nickel 3 or 4+. When not protected, some electrolyte species attack the surface. The surface 3 or 4+ is reduced to nickel 2+ with gas formation. The 2+ dissolves into the electrolyte, leaving defects and weakening the cathode surface. The protective layers prevent nickel from being attacked by harmful substances. Moreover, the highly oxidative species, such as nickel 4, is isolated so it cannot oxidize electrolyte in contact. These all contribute to a longer cycle life of the cell. The authors reported results from very systematic comparison among particles prepared in different ways. For example, Nyquist plot shows that when cells are constructed in the same way, the multilayer coated NCA single particles exhibit lower interfacial resistance than that of the uncoated ones. The lithium-ion diffusivity measurement is done by using GITT method. The conventional NCA particles without coating show the lowest diffusivity, while the particles with full coating documented in this patent show the highest. It's worthy mentioning that when lithium phosphate is removed from the coating, the diffusivity decreases. It's because lithium phosphate serves as an ion-conducting but electron-insulating barrier that allows lithium-ion transfer. At the same time, it inhibits unwanted electron conduction, minimizes parasitic reactions that contribute to resistance buildup. In terms of capacity retention, coated particles behave significantly better than that of the uncoated comparative example. It seems that a slight increase in firing temperature with longer duration does produce particles with better stability. Example number 6, with 825-degree heating, exhibits a capacity retention of 92.7%. Further increasing the temperature by 25 degrees to 850 degrees shows significantly improved capacity retention to 96.7%. So why does this matter? This patent represents an industrial effort toward the beautifully detailed development of artificial cathode-electrolyte interphase. A carefully engineered CEI helps reduce the degradation, including electrolyte oxidation, transition metal dissolution, and surface reconstruction. With minimized material degradation, the cell can achieve higher operation voltage, thus higher energy density. With less uncontrolled reactions at the cathode surface, there's less chance to get gassing, heat, or thermal runaway. Finally, by suppressing side reactions and minimizing irreversible loss of lithium or other charge carriers, the battery retains its capacity over many more charge-discharge cycles, resulting in a significantly longer operational lifetime. And, as always, I'll keep tracking these updates so you don't have to. Thanks for watching. If you're as excited about batteries as we are, hit like, subscribe, and stay tuned for the next episode.